In this video, we're going to generalize the idea of the ring of polynomials. We've already talked at some point about rings of polynomials like z bracket x and r bracket x, and those represent the rings of polynomials with integer coefficients and real coefficients respectively. But actually, you can take a ring of polynomials over any commutative ring, and in this video, we're going to show how. So here's the definition. Assume R is a commutative ring. We're always going to assume commutative ring for this, otherwise things get kind of chaotic. So assume that R is a commutative ring. We define the ring of polynomials over R, which we will call R bracket x, as follows. So first of all, what are the elements of R bracket x? The elements of R bracket x are formal symbols of the form P of x equals something like this. Okay, so P of x is going to be a formal symbol of the form a0 plus a1x plus a2x squared, and so on up to am x to the m for some natural number m, where, and this is the fun part, because when we talked about polynomials over the integers, those coefficients had to be integers, and when we talked about the reals bracket x, those coefficients had to be reals. So this time, the coefficients a0, a1, a2 up through am, those are all going to be elements of our ring R. So those are elements of R. And one thing we're going to do just as a matter of convenience, when we see this P of x defined as the sum of a0 through am x to the m, we're going to assume that stops there, but we are also going to assume that if we need to talk about coefficients a sub n, where n is greater than m, we can do that. And here's how we do that. And we define, I'm going to call it a sub I, to equal 0 for all I greater than m. So in other words, if I talk about, say, a sub 7, and you don't see a sub 7 here, you don't see terms beyond like the 5th degree term, then a sub 7 is just 0. Okay? So anyway, here's how we define operations in R bracket x. So to define addition, if P of x is equal to, let's call it a0 plus a1x plus up through am x to the m, and Q of x is equal to b0 plus b1x, and so on, up through bn x to the n, then how do I add those? Well, I add those the way that we usually add polynomials, which is by adding like terms. So we're going to define P of x plus Q of x equals this polynomial, a0 plus b0 plus a1 plus b1x plus, and so on, up through ak plus bk x to the k, where k is the maximum of m and n. And this is where that notational convenience comes in. Like, let's say that P of x has degree 3. In other words, the last term we see is a3x to the third. And then qx has degree 5, so we end with b5x to the fifth. Then P of x plus Q of x is still going to have a 5th degree term, and that 5th degree term is going to be a5 plus b5 x to the fifth. And we see here what b5 is, but since P of x only went through the 3rd degree term, what is a sub 5? And that's where this definition comes in. According to the definition, we just say a sub 5 equals 0 if there's no 5th degree term there. Okay, so that allows us to define addition that way without having to make any special provisions. Okay, so that's addition. And in multiplication, I'm going to assume that P of x and Q of x are the same thing, so I don't have to write those again. And we're going to say P of x, Q of x is going to be equal to, and I'm just going to write down a polynomial, and then we'll say what the coefficients are in just a minute, because this is actually a little tricky. All right, so I've just defined p of x times q of x to be this totally other polynomial, but then I need to say what the c's are, otherwise this makes no sense. So this is where c sub k equals the sum from I equals 0 to k of a sub k minus I times b sub I. Now, who in the world would come up with such a weird definition? What in the world is that? Well, here's the motivation for this. Anytime we define something in algebra, there's usually motivation for it. In fact, I would say there's probably always a motivation, even if it's not quite visible to us. But I can make this one very visible. We are used to multiplying polynomials. We have a strategy for doing it. Let's suppose that I have two polynomials. I'm going to make these a little bit nasty just to illustrate a cute method for adding these. So let's say we want to multiply 3 plus 2x minus 5x squared by 4 minus x plus, let's say, 7x squared. Okay, one way of doing this, one way of doing the multiplication is to do the distributive property. See, there's no FOIL here because there's no first, outer, inner, last. I mean, I guess there are first, outer, inner, and last terms, but that wouldn't be all of the terms of the product. So now we have to think, we got to distribute this, which means we have to multiply this term, 3, by each term of the second polynomial. We got to multiply 2x by each term of the second polynomial. We got to multiply minus 5x squared by each term of the second polynomial. There is a nice visual way of doing this that helps us to keep track of it, and it is to use a table. In grade school, they call this the array method of multiplication. We're not going to go into great depth on like why this works or what its education implications are. We're just going to use this as a tool to keep track of partial products. All right, so I'm drawing a 3 by 3 array here. And on the left-hand side of the array, I'm going to write down 3 plus 2x minus 5x squared. I'm going to leave off the plus signs just for simplicity. And then up top, I'm going to write 4 minus x and then plus 7x squared. And I'm going to use this to keep track of each term of this polynomial times each term of this polynomial. So keep track of all the products we get. So the products are going to be 12, and I'm just going to do these very quickly. 21x squared, and then we got 6x there, negative 2x squared. This is kind of fun, actually. Kind of fun sometimes to unplug and do something that doesn't require a whole lot of thinking, besides just multiplying monomials. There we go, 35x to the 4th. Okay, and then if we were to write down the product, we would actually gather up all the like terms. And look at where the like terms are in this array. This is the fun part about this. I have one constant term. I have 2 first-degree terms. I have 3 second-degree terms. Excellent. I have 2 third-degree terms and 1 fourth-degree term. So the sum I'm going to get is going to be 12, and then plus 8x minus 3x, that's plus 5x. Great. And then negative 20x squared minus 2x squared plus 21x squared. Oh, that came out really close to 0. That's like, that's going to be minus x squared. That was fun. And I've got 19, positive 19x to the 3rd, and then minus 35x to the 4th. And you can check me on that. Make sure, use Wolfram Alpha or whatever to make sure that that works out the way that I said it works out. But actually, the thing I most want to notice here is how this works in relation to this definition that we wrote down, because that's really the key point here. So the question is, why the formula above? And probably the best illustrative example here is to look at what we would have ended up calling c sub 2 in the above formula. C sub 2 is the coefficient of the x squared term in the product. And in this case, we got c2 equals negative 1. It's just negative 1. Negative x squared was that term. Okay, so according to our formula, c2 is supposed to be this. And I'm just writing down what this formula is telling us. It's the sum from I equals 0 to 2, because we're finding out the second degree coefficient, of a sub 2 minus I, b sub I. Okay, that's what the formula claims, but how do we actually do it in this example? Well, our two polynomials we could have called a0, and then this coefficient is a1, this coefficient is a2. Note the minus sign there. And then here we have b0, b1, note that's a negative 1, and then b2, that's 7. Okay, well, for our second degree term in the product, what did we have? We had negative 20, that's part of the coefficient, and then plus negative 2, and then plus 21. And where did each of those come from? The negative 20 came from 4 times negative 5. That was a sub 2, b sub 0. The negative 2 was 2 times negative 1, I believe. That was A1, B1. And then the 21 was A0 times B2. So what we were doing was we were just accounting for all of the different ways when we take this product that we could end up with an x squared. We could use the x squared term here and the constant here. We could use the first degree term and the first degree term. Multiplying those x's will give us an x squared. Or we could have the constant term here and the x squared term here. And those are the three ways that we can get a term of degree 2, or an x squared. So when we're looking at this formula, all that we're really doing is just accounting for all the ways that we could get x to the k in the product. There we go, x to the k. And we're just thinking, well, x to the k, that would be x to the k times 1, or x to the k minus 1 times x, or it'd be x to the k minus 2 times x squared. And we keep going, and the last possibility we get is 1 times x to the k. So those are all the different ways when we multiply that we can get x to the k, and each of these corresponds to one term of this sum. So I hope that illuminates that a little bit, because I feel like when we present this formula, it can be a little bit non-transparent. Anyway, so here's the big claim that's being made here. Because now we've defined a set, we've defined addition, we've defined multiplication, and now we're claiming R bracket X, even when R is some weird ring, this is a ring. And to prove that, we would need to show it has all the ring properties. We'd need to show that it has closure under addition and multiplication. That's not too hard to believe, though, because when we add two polynomials, what are we getting? We're getting a polynomial. This is certainly something that will be a member of R bracket X. When we multiply two polynomials, we get a polynomial. By the way, one thing I didn't really highlight here is we ended on C sub m plus n times x to the m plus n. And the whole idea there was, when we multiply p of x times q of x, well, the maximum power of x, p of x has is x to the m. The maximum power q has is x to the n. So we're not going to get any power higher than x to the m plus n. So that's why we stop there. So anyway, we have closure. We would need to show that addition and multiplication are both associative, that addition is commutative. Actually, that addition is commutative is not too hard to believe, because all of these little additions are taking place in R, and R is a ring, so its addition is commutative. So no problem there, really. We need to show that there is an additive identity. We'll just write down what that is. The additive identity is the polynomial 0. So in other words, a sub I is equal to 0 for every I. And the multiplicative identity, assuming that our ring has unity, I don't think I said that we did, but if we do, the multiplicative identity will just be the polynomial 1. That is the one where a0 is 1 and ai is equal to 0 for every I greater than 0. In other words, every term beyond the constant term is 0. We will have additive inverses because R contains additive inverses for every coefficient we might come up with. Typically, we will not have multiplicative inverses for things. That's much trickier. We might have them for the constant polynomials, but probably nothing else. And finally, to prove that R bracket X is a ring, we would need to show it has the distributive property. And actually, the way that we defined multiplication, we defined this in such a way that this ring would have the distributive property, with X acting like just another ring element. I mean, there are other ways that we can define multiplication that will pretty much give us a ring. For example, we can define multiplication by just multiply the, let's see, where are we? Multiply the 0th degree coefficients, multiply the 1st degree coefficients, multiply the 2nd degree coefficients, and so on. But then we get a ring structure that's really just a direct product of a bunch of R's together. This X isn't really playing a natural role algebraically. So we wanted something more like this, so that X would behave like a natural ring element, a ring element of R bracket X. Okay, so anyway, I'm not going to go through all those proofs that R bracket X has all the ring properties. Those are things that you can do on your own. For now, we're just going to assume that R bracket X has all those properties. But one more thing I want to define here, it's going to be useful for our analysis of this ring, is that if P of X is equal to a0 plus a1x, there we go, plus a2x squared, up to amx to the m, and a sub m is non-zero, that is, a sub m is the last non-zero coefficient of p of x, then we say the degree of p of x is equal to m. That is a definition there. So we define the degree of p of x to be the index of the last non-zero coefficient. In other words, if we say p of x has degree m, we're saying it has an x to the m term, but no greater power of x in there. And that's going to be really useful to us when we start proving things like the fact that if R is an integral domain, then R bracket x is an integral domain. More on that later.